nice bright day. We had some good lighting, so I figured, you know what? Why don't I make a new video? This is about black holes again. On today's, what I wanted to do is to try to give you I want to try to give you a realistic viewpoint of what's going on with these things. So far in some of the videos we've gone over how they get made, what happens to the subatomic particles and the parts of the atom when they dump into these things. Today what I'm going to talk about is the sizes, right? Because this is important. Just to give you an idea, something like the sun, right? If the sun were to collapse, it would become a 3-kilometer hole or a 3-kilometer sphere. So just imagine something the size of the sun shrinking down to 3 kilometers. Now, usually, well, not usually, the rule of thumb is, in order to get that sort of gravitational collapse, you need 3 solar masses, right? So with 3 solar masses, what you're going to get is, they go by the radius. And the reason they go by the radius is, if you just think about observer dependence, depending on where you're at around this object, at any point around this object, from any side, the top, the bottom, the side, your radius is going to tell you how far you are from the center on any side. And then, of course, with your diameter, you're going to double that, because a sphere goes out in every direction. So with the 3 solar mass, what you're talking about is a 9-kilometer radius from any point, which will make the hole have about close to an 18-kilometer diameter. All right, now you could do that calculation. You can go on Google or calculator and you can figure out how many miles that is, but it's very small. In the center of our Milky Way, we have a pretty good size black hole. Sagittarius A is about 4.3 million solar masses. And this thing's gravitational power can go out to 100,000 light years. So just imagine something like that, like a star that collapses that has that much solar masses to it, that many solar masses to it, can actually control a time space for 100,000 light years. That's pretty amazing, considering. And of course, physicists, there's been so much work that's been done over the years. It will take you decades to study, to go in and to learn about, Feynman diagrams, Fermi-Dirac statistics, just all the different mathematicians, Bohr, Born, Schwarzschild, Oppenheimer, Chandrasekhar, all the physicists and mathematicians that all put their 2 cents in to figuring this out. And of course, they built a little bit and built a little bit and built a little bit and had progress and built progress on top of progress. And now we've arrived at where we're at, which is science has a pretty good understanding of what these things are and what they do. But the one in the center of our galaxy is actually 26,000 light years away. Which means even if me and you had a rocket and we could take off at light speed right now, it would take 26,000 years at light speed to get to this thing. So you're in no danger of being anywhere near it. That's the first thing. The second thing is our star, and we don't have really any stars that close to us. There is a couple that are several thousand light years away, but again, that's a long time at light speed, so we're not in any danger of getting sucked in by any. They do believe, though, that there are primordial black holes that existed since the Big Bang, little tiny ones. And they could be responsible for dark matter. Like, we don't know. It's still up in the air as to like whether it's really dark matter or not. But these things evaporate, and so if they don't have any food, if their gravitation can't pull anything in and they can't keep eating, they evaporate through Hawking radiation. It's a very slow process and it takes a long time. But if black holes formed right after the Big Bang, and they've had almost 14 billion years to evaporate, of course that's a long time. So some of them probably shrunk almost down to nothing and are probably pulled in by something else's gravitation at this point. And, you know, depending on size of the mass, temperature and pressure, what kind of stuff they're coming up against, it's not like they can just eat everything, you know what I mean, real quick. So they're not going to be able to just gain in size so fast. But they could be adding to the total amount of mass that we, and physicists can tell that there's extra mass there, because the best example would be Andromeda and the Milky Way. Well, Andromeda, it has a bigger, it's an elliptical, it has a bigger swath, okay, that it takes up, and it has about 1 trillion stars, whereas the Milky Way has about 400 billion. So it's got more stars, and it has 140 to 240 million solar mass black hole in its center. So we know it contains a lot more mass in terms of the luminous matter you can see, but the Milky Way isn't equal in every way, and they can tell this gravitationally, that the Milky Way is indeed a heavyweight, just like Andromeda. The only thing is they can't physically see the mass. So they basically know that there must be either dark matter or some large amount of mass that is there in the Milky Way that makes it a titan, just like Andromeda. But yeah, with the neutron star, you can just picture a star, you know, it has a very high energy content density. It's gooey, it's a plasma. When that thing gets to the end of its life cycle and it collapses, 1.4 solar masses will give you your neutron star. So that's going to be an incredibly hot, incredibly dense, and small hunk of mass with a really, really high thermal value. But at a point, mass can become like an insulator, if you think about it. You know, like you just keep adding coats and adding coats and adding coats, you get hotter and hotter and hotter. But if you added so many, okay, that it crushed the mass so much that particles can't move around and bump into each other, all right? A lot of the kinetic energy that they derive up from being crushed together goes out the window, because now things get too still. And this is what happens with the crushing gravity of a black hole, is that it actually crushes the mass to the point where it can no longer express a thermal value. So the temperature goes down to absolute zero. And that's the point at which all molecular motion ceases. That's the point where time stops. Because you can't have time. If you can't have electromagnetic force and you can't measure anything, you can't move independently, you have no way of telling time. So, interesting stuff.